Imagine watching a planet die. Not reading about it happening billions of years ago, not modeling it on a computer, but actually pointing a telescope at a real world right now and watching it come apart piece by piece. That's not a hypothetical. It's happening twice in two completely different star systems, and the James Webb Space Telescope has been watching close enough to catch the chemical wreckage streaming off both of them. Scientists studying this have called the process utterly cataclysmic, and once you understand what these two planets are actually going through, that word choice starts to feel like an understatement rather than an exaggeration. Stick around, because this is one of those rare cases where astronomers got extraordinarily lucky with their timing, catching two worlds in what might be the final chapter of their entire existence. And if you want to catch every new discovery like this the moment it happens, go ahead and hit follow before we get into it. For most of the history of astronomy, studying what a planet is actually made of on the inside has been almost impossible. Even here on Earth, humanity has never drilled more than a handful of miles beneath the surface, a tiny fraction of the distance down to our own planet's core. For a planet orbiting another star entirely, direct sampling has always seemed completely handful of miles beneath the surface, a tiny fraction of the distance down to our own planet's core. For a planet orbiting another star entirely, direct sampling has always seemed completely out of reach, something scientists could only estimate indirectly through mass, size, and rough composition models. But every so often, the universe hands astronomers a shortcut, and that's exactly what's happening with these two planets. Both are being torn apart by their own host stars, and as they disintegrate, they're essentially performing their own autopsy in real time. It's spraying their internal material directly out into space where a sensitive enough telescope can actually study it. The first of these two dying worlds is called K2-22b, a planet roughly the size of Neptune, though nothing about its situation resembles the cold, distant giant sitting at the edge of our own solar system. K2-22b orbits its star at a distance so close that it completes an entire trip around it in just 9 hours. To put that into perspective, Mercury, the innermost planet in our own solar system, takes nearly 3 months just to make one full orbit of the Sun. Being locked into an orbit that tight comes at an enormous cost. Surface temperatures on K2-22b climb past 3,300 degrees Fahrenheit, more than hot enough to melt solid rock, and more than hot enough to push straight past, melting into full vaporization, turning the planet's own crust directly into gas. Astronomers had suspected for years that planets like this might exist, based on strange, irregular dips in starlight as certain planets passed in front of their stars, patterns that didn't match the clean, predictable transits of a normal, stable world. But confirming exactly what was happening and figuring out what that escaping material was actually made of required an instrument capable of picking apart incredibly faint chemical signatures from many light years away. That's precisely the kind of job the James Webb Space Telescope was built for, and when researchers led by Penn State astronomer Jason Wright and graduate student Nick Toucey finally turned it toward K2-22b, they got their confirmation. Trailing behind the planet, sculpted by gravity and heat into an extended, comet-like tail, was a stream of vaporized rock, the planet's own surface material boiling away and stretching out into space behind it as it raced along its 9-hour orbit. What genuinely surprised the research team wasn't just that the tail existed, it was what was inside it. Webb detected gases like carbon dioxide and nitric oxide mixed into that trailing material, chemical signatures typically associated with icy, volatile-rich bodies, not the solid, rocky mantle of a terrestrial planet. Under normal circumstances, gases like these should have boiled off a rocky planet's surface and vanished long ago, not still be actively present today. Toucey later summed up his reaction to the data in a phrase that captures the moment perfectly, describing it as a genuine who ordered that kind of surprise, the sort of result that raises more questions than it immediately answers. Researchers now suspect K2-22b likely didn't form anywhere near the scorching orbit it currently occupies. The leading theory suggests it originally formed much farther out from its star, in a colder region of the system where those volatile gases could have remained locked safely inside it, before gravitational interactions gradually dragged the planet inward to the brutal orbit it holds today. That kind of migration becomes especially plausible in this particular case, since the star K2-22b orbits shares its cosmic neighborhood with a companion star, whose gravity could plausibly have helped nudge the planet inward over time. If that theory holds, the material streaming off K2-22b right now isn't just evidence of its ongoing destruction. It's a kind of chemical time capsule, preserving clues about a much colder, much calmer origin the planet left behind long before ending up here. The second dying world in this story carries a genuinely unsettling title of its own. It's called BD+054868Ab. and it holds the distinction of being the closest known evaporating exoplanet ever discovered, at least so far. Unlike K2-22b, this one wasn't found through Webb directly, but through NASA's Transiting Exoplanet Survey Satellite, known as TESS, which specializes in detecting the telltale dimming that occurs when a planet crosses in front of its star. And what TESS revealed about this particular planet was even stranger than K2-22b's single tail. BD+054868Ab has two separate tails streaming off. It's simultaneously a leading tail made up of larger, sand-sized particles racing out ahead of the planet along its orbit, and a distinct trailing tail made of much finer, soot-sized grains dragging along behind it. Combined, these two tails stretch across roughly 5.6 million miles of space, spanning nearly half of the planet's entire orbital path. The sheer scale of destruction happening to this world is almost hard to process. Researchers estimate BD+054868Ab is currently losing roughly a moon's worth of material every single million years, an extraordinary rate of mass loss for any planetary body to sustain. At that pace, astronomers calculate the planet has somewhere between 1 and 2 million years left before it's fully consumed and ceases to exist entirely. Compared to the billions of years most stable planets persist for, a window of 1 to 2 million years is an almost impossibly narrow sliver of time. And yet, that's the exact moment astronomers happen to catch this particular world in. MIT postdoctoral researcher Mark Hahn, who led the discovery of BD+054868Ab, described the significance of witnessing this moment in stark terms, noting that the rate of evaporation is utterly cataclysmic, and that the research team considers itself remarkably fortunate to be watching what amounts to the final hours of a dying planet. Given how vast the typical timescales of planetary science are, actually stumbling across a world in the last 1 to 2 million years of a multi-billion-year lifespan is an extraordinarily rare thing to witness, let alone catch with instruments sensitive enough to study it in real detail. What makes both of these discoveries so scientifically valuable goes well beyond the raw drama of watching two planets die. It's what they're revealing about something normally completely hidden from view, the actual internal composition of a rocky world. Wright, one of the lead researchers behind the K2-22b findings, described the situation as a remarkable and fortuitous opportunity to understand terrestrial planet interiors, information that would otherwise remain almost entirely theoretical, built on models and inference rather than direct observation. Toussaint framed it even more bluntly, explaining that these two planets are essentially spilling their own guts into space, and that Webb finally gives astronomers the tools needed to study that material directly and figure out what planets around other stars are genuinely made of. Both sets of findings, the detailed Webb-based observations of K2-22b and the TSS-driven discovery of BD+054868Ab, were released as research papers that were still undergoing peer review at the time they were first announced, meaning the broader scientific community continues to scrutinize and refine exactly what these results ultimately mean. But even at this relatively early stage, the implications are already reshaping how astronomers think about the eventual fate of planets that end up trapped in extremely close, scorching orbits around their host stars, whether through their original formation or through gradual gravitational migration over time. There's something genuinely striking about the narrow window both of these discoveries represent. Each of these worlds is caught in an extraordinarily brief, violent phase of its own destruction, a process that, measured against a planet's typical multi-billion-year lifespan, will be over almost as soon as it started. Every observation astronomers manage to collect from these two systems right now represents data that will simply cease to exist the moment these planets are fully consumed. Information about planetary interiors that has no other way of ever reaching us once the material scatters into the void for good. It's also a genuinely humbling reminder of exactly how unforgiving orbital mechanics can be. Both K2-22b and BD+054868Ab stand as real-time, real-world examples of what eventually happens to a planet that ends up locked into an orbit its star was never going to let it survive. Watching that process unfold isn't just a striking visual. It's handing scientists an unprecedented data set on planetary composition, planetary migration, and the surprisingly violent way a planet's entire story can come to an end, all captured by a telescope purpose-built to detect exactly this kind of faint, fleeting chemical signature from many light years away. So right now, K2-22b continues tracing out its 9-hour orbit, trailing a comet-like plume of its own vaporized rock behind it as it races around its star, while BD+054868Ab counts down what may be the final 1 to 2 million years of its existence, spilling sand and soot into space along two separate sprawling tails. Neither planet has any realistic chance of surviving what's happening to it. But in dying, both are handing astronomers something genuinely priceless, a direct, real-time look inside the composition of a rocky world, delivered not through theory or simulation, but through the simple, brutal physics of a planet being slowly consumed by the very star it once orbited peacefully. If a story like this, catching two entire worlds in the final act of their own destruction and turning that into genuine scientific insight, is the kind of thing that genuinely fascinates you, go ahead and subscribe. Drop a comment letting me know which of these two dying planets stuck with you the most, and stick around, because there's a real chance Webb catches another one of these rare, fleeting moments sooner than anyone expects.